Hello, my name is John Mad Dog Hall. I'm the board chair of the Linux Professional Institute, the senior advisor to Caninos Lucas, the president of Project Kawan, and the president of Linux International. My talk today is about security, and that basically, if you don't have free software, you really don't have IT. I'd like to dedicate this talk to Alan Turing. He was a mathematician, a cryptologist, a philosopher. He's generally regarded as the father of computer science and artificial intelligence, and he was a war hero that he reduced World War II by approximately 2 years and saved an estimated 14 million lives by decrypting the German Enigma code. For those of you who are not familiar with me, I've been in the computer industry since 1969. I've worked on a variety of different operating systems. I've worked on a variety of different companies, some small, some large. I've been a variety of different jobs inside of those companies. I taught operating system design, compiler design, and database design at the university level. I've worked on extremely large systems and extremely small ones. I've been both a vendor and a customer, and I like to think of myself as being pragmatic. So even though I believe that free software is a way to generate software and generate solutions, I do not spit on people if they feel they really need to use closed source software. I'm going to give you a series of talks which I call Mad Dog's Real Life Stories. Back when I started into programming, there was no real networking, unless of course you wanted to carry a box of cards down the hallway. And printing and graphics was basically doing ASCII art on a line printer. Security was locking the computer room door when you went home at night. And yes, you did turn off the electricity to the computer because if it burned up, well, that was a lot of money. So that's the way it was when I started out. Now, there were these two guys. One person was named Ken Thompson, and he was the co-founder of Whonix in 1969. Murray Hill, New Jersey, worked for Bell Laboratories. And we found out that he could actually break into any Unix system almost as fast as you could log in. He would just sit down at the console and type a few things and break into the system. And nobody could figure out how he was doing it. There didn't seem to be any trapdoor in the operating system sources for Unix. They couldn't find any trapdoor in the login program. They say, oh, maybe he put it in the C compiler. But they looked at the source code for the C compiler and they didn't find anything. And no one knew how he did it. And finally, many years later, he confessed to how he did it. He actually put the trapdoor into the object code of the C compiler. And when the C compiler saw that it was compiling itself, it put the source code for the trap into the source code for the compiler. It compiles the compiler, and then it erased the trapdoor from the source code of the compiler. But by that time, it was too late. And so that's how he did it, and nobody could figure it out until he actually told them. I would like to talk to you about a little program called Hacker Team. A friend of mine in Sao Paulo, Brazil, was in his office one day, and the Brazilian FBI called him. It turns out that there was somebody who was breaking into a bank, and they had found where this person was. They'd gone to the house. They asked for the person by name. And a 10-year-old boy said, well, that's me. And the FBI couldn't figure out why this 10-year-old boy was doing this. And so they asked my friend, and my friend says, well, I don't really know either. And so my friend called me up, and I said, well, this person is a script kiddie. They go out onto the internet, and they look for people who are writing code that break into other people's systems. They grab a piece of code, a script, and then they apply it against thousands and thousands of systems trying to break into any one they can just so they can brag to their friends that they had done it. And of course, once they do that, their friends turn them in and get them in trouble. So my friend thought about this for a while and he says, well, what would happen if I took these kind of at-risk kids and taught them how to be good computer people, gave them training in security and training in systems administration and training in ethics. And I actually had them talk with psychologists and things like that so that they get them on the right path. And he created this program called Hacker Teen. And he used Japanese cartoons, anime they're called, and he even had a book done about Hacker Teen where they created various examples of programs and had the kids work together to solve the problem. And he had hundreds of kids go through this program, and a lot of them became very good computer people. Unfortunately, Hacker Teen didn't last as a program as long as we would want it to, but it's an example of what can be done when you treat people in a positive way. I had a friend who was teaching at a high school, and they asked me to come and talk to them about free and open source and Linux in particular. So I took along some CDs to hand out to some of the students. They didn't bring me all of the students, just some of their very good ones, and we had a talk about free software. And most of the people in the school were using Apple computers because the school had a lot of money and they liked Apple computers. So I gave out these CDs to the students, and they booted their CDs upon their laptops and their desktops and things like that, and everything was fine. A couple days later, the systems administrator called me and was kind of a panic. They said, with those CDs, you can actually look at all of the data that's stored on our Apple server. It just ignores the Apple security altogether. And this is terrible. I says, well, it may seem like it's terrible to you, but at least now you know that it can be done. And so it's better that you know it can be done and can protect against it than not know it can be done and blithely go on. I had this gentleman, his name was Paul. I never knew his last name. He was one of the customers that a salesperson brought me. And he said, John, this is Paul. And I says, oh, nice to know you, Paul. What do you do? And my friend said, if he told you that, he'd have to kill you. Now, my friend was kind of joking about that, but not so much so, because Paul worked for one of those companies that we dare not say their name. I should say agencies, that we dare not say their name. And my friend told me to tell Paul everything I knew about Alpha and Digital Unix, which hadn't been announced yet. He said, don't worry, because anything that goes into Paul never comes out of Paul. So I told him everything I knew, and Paul just sat there and kind of nodded his head and smiled. He was a kind of a chubby man, older, very nice personality. And in the middle of my conversation, Paul looked at me and said, that's really wonderful. Do you think we could rack mount those and put them up and fly them around in an airplane? And I says, well, you could do that, but you need to have a really good power supply. Paul kind of smiled and said, well, don't worry about that, which is really the only indication I ever got out of Paul as to why he was interested in our systems. A few years later, I was at a Usenix conference and I recognized Paul. And I went over to say hello to him, and his name badge says Paul, a government agency. And standing next to him was Sam, and his name badge says Sam, another government agency. And the reason I'm telling you this story is because these government agencies have a lot of money and a lot of expertise, and they can actually break into a lot of systems that you think are very secure. This is my last story. It's about a friend of mine named Nick Walker. I first met Nick at the age of 15. He lived close to my house. He sent me this email that said, hi, I know that you're working with Linux and I really like Linux and I was wondering if we can get together. I said, of course we could. We could have some pizza and beer. He says, well, the pizza is good, but I'm only 15, so I really can't drink beer. And I became good friends with Nick. We did quite a bit of things together. I took him out to some universities to see if he really wanted to go there. He had finished every class he could take in high school, and there was nothing else he could do. So he was working for his father, writing device drivers for Linux and being paid about $40,000 a year to do that. He eventually went to this university called Simon's Rock School of Bard, but instead of matriculating at the university, he became a network administrator for them, redesigned their network. One day he saw some hackers trying to break into the network. He formed a honeypot, trapped the hackers in that, making them think they had broken into the network, but they hadn't. He then called the FBI, and the FBI traced them to Italy. These people were arrested in Italy, and this generated a two-page Business Week article about my friend Nick, free software, the advantages of using it, and all sorts of other things. He had not reached the age of 21. So with all of that, what is free and open source culture, and why should you pay any attention to it? We're going to start with the concept of public domain software. Back in the early days of software of all types, you could not apply copyright to the software. So if you wanted to protect it, your intellectual property, you had to do that with contract law. And the contract law, you would write a contract saying this is what you can do with this piece of software, and the other person would have to sign it and agree to it. But this was a lot of work, and so a lot of people, when they wrote their software, they just said, okay, I'm going to put it in the public domain, and anybody can use it for any purpose whatsoever. A little while later, copyright started to be applied to things like computer game ROMs, and later on to the source code that created those ROMs. And people started applying that, and also to patents on ideas for this code. And in the beginning, contract law then acted as a license, but eventually there was, that got to be rather bulky, so people invented something called the End User License Agreement, or the EULA, as we call it. Closed source software was a way that people would try and sell software and make money, and they felt that the closed source protected their intellectual property along with the copyright laws and things like that. Open source has two main types of licenses. Open source means that we're going to make the source code available to people, and we have two different types of licenses. One is called permissive, which means that there's very little restrictions on you for what you do. If you want to use the source code, you can for all sorts of purposes. And licenses that go along with this are like the BSD license or the MIT license, which are educational universities. Then we have another license, which most people call restrictive. And that says that there are very specific things that you have to do if you're going to use the source code for this source code. And these licenses are represented by things called copyleft or share alike, or the Free Software Foundation's GPL, General Public License. Then we have the concept of open culture or Creative Commons, which is licensing applied to text or film or videos or photographs or audio files or things like that. And we'll get a little bit more into that later. And finally, in the later years, this has also come down to hardware. Now, of course, hardware is different because it costs money to make hardware things, versus making a copy of a piece of software is extremely cheap, less than half a cent. So the open hardware may have certain parts of it which are a little bit more closed than normal. But if you want to talk about completely open hardware, then it's hardware that has to have the circuit diagrams available, and the data sheets for all the controllers on it have to be available. so that you will be able to program this device far into the future. You might want to be able to publish your bill of materials. What parts go onto the printed circuit board, and where do you get those parts? And finally, you may print out the printed circuit board itself using something called Gerbers, which allows you to make the printed circuit board, but also talks about the layout of components on that printed circuit board in case people want to make cases for it and things like that. Now, a lot of people say, well, free and open source software, hardware, and culture, that's new stuff, right? That's only in the last 20 years, 30 years. No, actually, early software was often distributed in source code. It was written by people who needed to have the software for themselves. And even if they were writing it for somebody else, they would bring the source code and compile it and qualify it on site at the customer's site, because each computer was a lot different than the other one. And there was no standard operating system that went across them. So you sometimes had to change your source code in order to get the product to actually work. And once that was done, the person who bought the software owned that copy of the software. And they could do stuff, they could change it if they wanted to, they could hire a third party to fix it if they needed to have that and they didn't want to go back to the original vendor. This was protected by contract law, as I said before, and you might have to pay $100,000 for a single copy of, say, a compiler that was going to go in a single system, be used by one programmer at a time, maybe in a batch mode. And that was, of course, a lot of money. But if that compiler made your code run 10% faster, and it was going to go on to a $2.5 million machine, then you could see that it was a good deal. The return on investment was good for that. And of course, back in those days, at the same time, the hardware was not even put onto a printed circuit board. It was a lot of times built by hand on what is known as a perforation board or other type of backplane, and wire wrapped instead of soldering to put the conductors in place. But in the early 1980s, people were starting to create games, and a lot of the game ROMs were being copied by people. So if you were a competitor to the game company, you would buy one copy of the game. You would then look at the board, figure out how it was wired, and you would duplicate the board. But the game inside the ROM also had to be copied. And of course, this was bad for the company that originally made the game because they put a lot of work and effort into it. They expected to sell and get return on that. The people who were just copying it, they didn't really have to spend a lot of money on that. They just reverse engineered the board, manufactured it, and copied the ROM. So people went to various governments and said, we need to be able to copyright that ROM to protect our intellectual freedom. And so copyright was applied to the ones and zeros for the first time. Later on, they said, well, it's the source code that makes the ones and zeros in that ROM, so we need to be able to copyright that also. And finally, out of all of this came something called the End User License Agreement, which allowed people to distribute the ones and zeros or the source code. And if you opened up the package, then you automatically accepted the terms of the End User License Agreement. Now, this also affected universities. Universities have been putting out their software, publishing their software, and basically putting it into the public domain. They really didn't care that they got paid for this because it was a byproduct of their education. However, when copyright happened, now all of a sudden the universities found that they had to specifically say it's okay to use the code, because people were afraid that they would be sued for copyright infringement. And to do that individually, was a big pain for the universities, particularly if they were not going to charge for it. They're not looking at any revenue. And so they go in and they say, okay, we're going to create a license and we are going to put that in the source code of the code that we're distributing. So if you can see the source code, you can see this very permissive license that says, yes, you can use the source code, you can copy it, you can change it, what we call derivative works. And, oh, by the way, because we're giving it to you free, we don't want you to come back and sue us if this software doesn't work or if it does some type of damage. So the license also limited the liability of the university for the software which they were distributing for free. And the Berkeley software distribution of the University of California, Berkeley was one of those. A little bit later, MIT also started to put a license in there that was slightly different. It made certain requirements of how you gave attribution to the software and how you exchanged it, how you compiled it. But basically, everything was wide open. And there was lots and lots of these different licenses, some of them having little tweaks that made them a little bit different. A few of them not having any real changes at all. They just changed the name of the license, maybe the Fred, base license or something. And this created problems because of lawyers who would see a new license, have to study it and make sure it was okay for their people to use it with all the other software that they were generating. And this created a problem because the lawyers are spending all of their time looking at licenses that may only have varied by the name. And so the Open Software Initiative came through and made some open source licenses, groups of them saying, please use one of these licenses. Don't invent your own. Don't make a license with your name on it because it just upsets the apple cart. And so that happened. Now, there was one person who really liked to see the source code for free software for Unix systems. And what was happening was that a lot of the companies who were putting out Unix systems as source code were now starting to put out binary-only code. And so you needed to have a license that not only allowed people to make the software, but also made sure that if the software was changed, those changes would be passed on to the end user. This is known as copyleft, as a play on words for copyright. It's also known as free software. And this was started in the mid-1980s by a person named Richard Stallman of the GNU project. GNU is an acronym for GNU is not Unix, because Unix you paid a lot of money for, and Unix you got as a binary standard, but this was open source and you didn't have to pay for it. And the two licenses that came out of that, the two main licenses, were the GPL, the General Public License, and the LGPL, normally used for libraries and things like that, called the Lesser General Public License. And these two licenses require that anybody distributing binaries to other people have to tell them where the sources are, have to tell them how to build these sources to make a viable system. And this has to be done to the people who receive the binaries, the end user customers. This was typically called viral by Microsoft and people from Microsoft. They hated it. They thought of it as a virus. And so that's where that came from. Now, another thing you can do is have dual licensing or multiple licensing. Let's say that there's somebody who comes along and says, gee, I like your code, and it's GPL, which means I have to make my changes to it known to everybody, but I don't want to have to do that. I want to keep my changes unique to myself, but yet I still want to use the GPL code. Well, you could do that if you went back to the original copyright holder and said, I want to have a different license for this. I want to have maybe an open source license for this, or I want to have it as, license it to me as public domain so I can do anything I want to with it. And this is a perfectly viable business model that you can give away the code to the free software community. They can work on it, they can make changes to it and things like that. They give it back to you and you incorporate those changes. And that way people can, have the free software. But if a person says, I really don't want to make my changes available to everybody, then they can pay you money to get a second license, and this helps to fund the project. But it's actually the same code minus the changes which these people made. Now, another interesting concept is called loosely coupled products. A while back, there was a little system called a Cobalt Cube. And the little Cobalt Cube would have a disk in it. It would have a single board computer. Might install Linux as the operating system on it. And then you would run Oracle database engine, which of course is closed source, on top of that. And the question came up of, do you have to distribute the source code for Oracle just because you're using that with a free software operating system? And the answer is no. What you have to do is you have to tell people in your manual for the product that if you want to see the source code for Linux, you can see it there, or you can get it off the web or anything like that. But you don't have to distribute the source code for Oracle because Oracle is only loosely coupled inside the box. And there's much, much more to all of this, except we really don't have time. And so if you want to study what the different licenses are and things like that, there's many books on the subject of how they interact. So because this talk is mostly about security, we're going to ask the question that's always asked, which is more secure, closed source or open source? And the argument for closed source is that, of course, you can't see the source code. You can't see the holes in the source code. So you have security through obscurity. We're going to obscure the way that the program works, and so people can't figure out if there are holes in the security model. The other hand, there's open source. People say, well, many eyes can see the issues, and so you're more likely to fix the problem, or people are less likely to insert a trapdoor, like Ken Thompson did, or, create a hole in the software because they'd be more likely to be seen that they had done that. Now, in reality, neither one of these are more secure than the other. I mean, if you say that closed source and security is to obscurity, well, then Microsoft would have the most secure operating system on the face of the earth. And that's simply not true. And so the real thing about all of this is neither is inherently more secure than the other. However, the thing that's good about open source is it has a shorter time to fix, a shorter mean time to fix. And so once you understand the problem and you understand what the trapdoor or the hole is, you can now take the source code, fix the problem, and get it working in a much shorter time than typically a commercial company could find the problem, get the engineer to solve it, actually write the patch, distribute it to their customers, and oh, by the way, maybe that's only on one type of hardware, not all the different hardware that the customer that exists and that the operating system runs on. So, but if you have the source code, you can compile it for Intel, you can compile it for ARM, you can compile it for all these different operating system and hardware architectures because you have the source code. I'll give another example of this. A long time ago, there was this thing called the Morris worm. And what it would do is it would run through the email system called SendMail, And because if SunMail had been compiled a certain way, it made it vulnerable to this worm. And most people compiled SendMail that particular way. So when the Morris worm was released, it just went right through Unix systems, spreading from system to system, and these systems were crashing like flies. DEC, Digital Equipment Corporation, my company, had retired a particular operating system called Ultrix 32, and we had sold that business off to a company that they would do maintenance of these systems. Digital itself was not going to create any more bug fixes for Ultrix 32. They were finished with it. That was at the end of life. And I was working for DEC, and I knew that there were still people using Ultrix 32 even though we had dropped support for it. So I realized that these people's systems would be crashing. And I had to blackmail my management to go in and make the fix for those Ultrix 32 systems. I threatened to expose their systems to the world, and they went ahead and made the patch. But it took 3 weeks to make that patch, and during that time of that 3 weeks, those systems were crashing out in the field. But once they had the patch, they were okay. They would stop crashing. Now, in the meantime, the free software community also was plagued with this particular bug, this particular Morris worm. And what they did was they generated a source code patch in a 3-hour period of time. Then they distributed that patch up on the fledgling internet. And they did this in a period of 3 hours. So the free software community generated the patch in 3 hours, and the closed source community generated the patch in 3 weeks. And this is why InfoWeek magazine, for 3 years in a row, gave the prize for best support of an operating system, not to IBM, not to Hewlett-Packard, not to Compaq or DEC, but to the free software community. And they did that 3 years in a row, and at the end of those 3 years, they stopped giving out the award because they knew what the answer was always going to be. It was always going to be the free software community. Another example of this is Spectre and Meltdown, two bugs that happened relatively recently. Microsoft had dropped support for Windows XP at the time, yet there were still hundreds of thousands of systems still running Windows XP. Microsoft then created a patch for Windows XP for Spectre and Meltdown. I will give them credit for that. But after they distributed that one patch, there's no other guarantee that any other security holes will be patched. And that leaves people still using those systems, Windows XP, vulnerable to those new security holes. And there are people in governments and even the military that are still using Windows XP today. So this brings about the question, the upcoming question of Windows 10 and Windows 11, where, according to Microsoft, the solution for the hardware that will not be able to run Windows 11 because they don't have the facilities for running it is to run Windows 10, and that Microsoft will keep maintaining Windows 10 for a very long time. However, sooner or later, because it's a commercial company, they're out to make profits, and there will be no more profit being made from these systems, they will drop support for Windows 10, and the only thing they won't be able to do then is for the customer to buy a new system with Windows 11 on it, and for that person, the Windows 10 old system is now useless. So this is why we believe that the real solution to the upgrade to Windows 11 is to use free software, the GNU Linux operating system, for an example, or BSD, or one of the other systems. and put that on all of your equipment and then be able to maintain that throughout time with either binary patches from the distribution or source code patches as long as you want to do that. Now, we're also going to talk about the concept of free and open stacks. Everything being open so that you can better support your various hardware and software. We're going to start with the hardware itself, with what we call binary blobs. In various operating systems or in various pieces of software, you'll find areas that people are not distributing the source code for it, even if it's a supposedly open system like a new Linux. So a lot of times these binary blobs are in things like the BIOS on the board, or they're in binary device drivers, or they're in video drivers, like things from NVIDIA and things like that. And any one of these binary blobs can actually hide a trapdoor or a Trojan horse that would allow somebody to take over the control of the computer system without you knowing. These binary blobs will typically operate in what we call privileged mode. They'll have the power to go any place inside the system and do anything. And that's if they're a device driver or an accelerator of some type, or even the boot code. If we take a look at the boot code itself, they have something called the Unified Extensible Firmware Interface, which is going to be taking over from the BIOS that we traditionally have had, and that's a good thing. The BIOS has been around for many, many years, and it's too small. It doesn't cover enough. People have been working very hard to get around its limitations. So the fact that UEFI is going to replace the BIOS is a good thing. Secure boot, which is part of UEFI, is also a good thing, because secure boot will only allow you to boot a signed copy of the operating system. Once that is running, it will only load signed copies of software. So if an unsigned piece of software comes across the internet, either through an email or through a website or something like that, then the operating system will not run it because it isn't signed properly. The problem with UEFI is that currently you can only get a certificate for booting that one particular operating system from only one US-based vendor. And it's kind of clunky, quite frankly. So, and the other problem is, this is great if you're inside the United States, you're a US, this company is a very good US-based company and people trust them and things like that. But if you're outside of the United States, you don't maybe have as much trust over that company. Maybe the United States government will ask them to do something, and that's a problem. So there are some open source projects which will allow you to create your own boot code. One is called LibreBoot, and that even you can get devices today on the market that have LibreBoot installed into them. It's an open source BIOS. You can see what it's doing. Coreboot is another one. And there are other open source projects to allow you to boot your system with this. The problem is getting that code into your system in the first place. And so we will have to work on that. Now, if you go down a level from things like the operating system and the boot code, there's another place that could have a possible trapdoor. And we call this an attack vector. A lot of processors like the ones from Intel or AMD or what we call complicated instruction set computers, CISC computers, CISC. And these computers, for every machine language instruction, actually has a tiny little program called the microcode. And the microcode tells the hardware what to do when it sees that particular machine language instruction. The problem is that a vendor or an entity could create a chip with a trap door in the actual microcode itself, and you wouldn't even be able to see it. You could look at all of your programs. You wouldn't be able to see what the trapdoor was. You wouldn't know how to initiate the trapdoor. It would be something that only that entity who changed that chip, who changed that microcode, would know how to do. And they may have done that. And you say to me, well, Mad Dog, that would take a very powerful entity to make a whole chip with that hole in it. And the answer is, yes, I know that, but those entities exist. And again, you're less likely to run into them if you're in the United States. You're a United States citizen, you're protected by our Constitution and things like that. But if you're outside of the United States, you may not have all of that protection. And some of these entities, like Paul and Sam worked for, have a lot of money and a lot of opportunity to be able to stick these processors into your system. Now, other processors, for example, ARM, are known as RISC processors, reduced instruction set computers, and each one of these have a single instruction for a single clock cycle. There's no microcode. So basically what you see in that instruction is what you get. And because the instructions are simpler, you could actually, if you were able to see the drawings for the processor and the mass for the processor, you could actually see that the processor was exactly doing what you wanted it to. Taking that a step further, there's a particular type of processor called RISC-V, or RISC-V as people want to say it, that is an open architecture. So all the instructions of what they do and everything like that is open for everybody to see. And you could take that open architecture and you could make the masks so the fab would be able to make the computer for you. You'd be able to watch the process of it doing that. You'd be able to take those CPUs and put them on your board so you have complete control about what you're doing. In fact, if you wanted to, you could actually change the instruction set on the RISC-V computer. You could change some of the bits back and forth so that the instructions do the same thing. It's just they have a different opcode. And then you could build an operating system that would only work on that specific chip. And any programs coming in from the outside as binaries would not be able to run on that chip. They would not be able to figure out how the instruction set was different. And this could give you a much greater level of control and protection. And this, of course, is more than just the CPU. This could also be done with the GPU, the graphical processing unit, that people could change the microcode inside of the GPU, and the GPU has a lot of microcode. Or controllers like the USB controller or the Ethernet controller or the SATA disk controller. And actually, a lot of this started back in the days of the Win modems, where originally modems were just a piece of hardware and really had no real device drivers to them. But in order to make them cheaper, people said, we're going to substitute a lot of source code and a lot of software for doing much of the things that a modem really does. And that became a Win modem, and that created a whole bunch of angst because people didn't create the software a lot of times for Linux systems or for BSD systems or other operating systems. And so people had to use real modems instead of Win modems. Now, you could say, well, Mad Dog, I can't go to a fab plant. I don't have the money to go to a fab plant and get them to make me a special RISC-V CPU that has some instructions changed, some opcodes changed. I can't afford to do that. Well, the good news is that you can actually implement a RISC-V CPU by using something known as a field programmable gate array. And the field programmable gate array is a set of transistors and what we call gates, that can be organized by being programmed to actually be a CPU or an FPGA. I mean, sorry, a GPU or a controller of some type. It can be programmed to be any one of these things. And you could program the FPGA to be a RISC-V chip. It would probably run a little bit slower than if the chip was made as a standalone chip in a fab plant, but it could be plenty fast enough for being things like a gateway or some other type of secure system that's only running a certain piece of software that to give you protection. So, as an example of this, the University of Sao Paulo created a virtual GPU that could run all of the OpenGL test suite and all of the codecs that's normally used in a system. And they did it in a virtual way. So they did it using an FPGA. And this worked very well, even though it was only working under emulation when the students left the project. It could do fairly sophisticated graphics and very well. So what I would like to see is this project taken to completion and take the virtual emulated FPGA and actually reprogram it with the real FPGA to have a truly virtual GPU. And you could do the same thing with the CPU as we discussed before. Now, Linux and Unix almost always from the beginning was more secure than certain other operating systems. It wasn't designed as a single person system. It was designed as a time sharing system. You had to protect one user from another. You had to protect the kernel from the users. You had to protect the disk drives from everybody using them at the same time. So a lot of this protection was built into the system from the very early days. The networking to Unix systems was also relatively early. The TCP/IP systems that we use today was first developed, on Unix systems. Berkeley 4.1c had TCP/IP, and that was way before other operating systems had it. So it's not only the OS that you have to make secure. Obviously, you have to make your networking secure. You have to have procedures for security. It's not enough just to have secure operating system, but it certainly is a good start. And so, if we start to look at Linux systems, how can we make Linux systems secure? Well, one of the things we recognize is that encryption is our friend. A lot of people think that encryption is bad, that the bad people only use encryption and stuff. But in reality, good encryption allows you to have good authentication. And the very basis of good security is good authentication, proving who you are and that you have the right to do certain things. And over the years, I've written multiple letters to clueless politicians in the United States in particular, telling them that they can't outlaw encryption because if they do, we wouldn't have good authentication. And usually after I write these letters, maybe they're 4 or 5 pages long, I send them overnight mail. The politician will drop their law that they were writing about authentication. One of the most famous authentications is PGP, Pretty Good Privacy. And out of that came a free software implementation of it called GPG. And then there's other types of encryption methods. Now, you could break encryption, okay? There's no such thing as a completely unencryptable file or program. However, you can make it so hard and take so long to do it that people will go on to an easier target. And so What you need to do is to teach people how to encrypt and how to authenticate and get them to do it all the time. Because even a really crappy encryption is better than none. And if you encrypt everything, then your adversary is going to say, well, what should I decrypt? I can't decrypt everything. I don't have the computer power to decrypt everything. But that's okay. If they really want to decrypt what you have, then they do the normal thing of going to a court and getting a subpoena to force you to do the decryption. That's the way it should be done. People should not be decrypting things secretly, quietly, unbeknownst to you. So, in Linux, you can encrypt the entire disk or encrypt a particular disk partition. And then every time you access the data on that, it is decrypted for you. And every time you store something, it is encrypted for you. You also have commands to decrypt things file by file, specific files if you want to. And so you can see the name of the particular file and say, oh, yeah, I know what that is. I can decrypt that, with using a special key. Another thing that Linux has is what we call pluggable authentication modules, or PAM. These have been around for a number of years, and these allow you to authenticate a user to specific applications and say, oh, you're a bad dog. You get to run this application. Or maybe you get to run this application at a particular time. Or maybe you get to run this application on a particular day. And so you can set up the rules as to when these applications can run and under what circumstances they can be done. They can be used to mount and unmount file systems at particular times of the day, so that if somebody was to log into your system at night or get into your system in some way at night, they would not even see that file system having been mounted. And you don't need to modify any of the application code for this. It's strictly on a system level, files of set of rules, and this came from the Unix systems of authentication. Now, there are whole distributions of Linux which are aimed towards authentication and security. And one of the first ones was something called Security Enhanced Linux, SE Linux. It was first developed by NSA. And a lot of the Linux community said, well, you're trusting the NSA to make a secure system? Well, they'll know how to break it. And that's a false type of thing, because the NSA also needs a secure system. And they're going to work very, very hard to make it very, very secure. And the Red Hat distribution of Linux supports this as a service. So you can install Red Hat and have it running Security Enhanced Linux from the very get-go when you're installing it. Another way of doing this is called AppArmor, and this is used by other distributions of Linux like SUSE or Ubuntu. And Debian 10 actually has AppArmor enabled by default from the very beginning. AppArmor works more on an individual program basis, much like the PAM modules do. In addition to all of this, maybe you want to try and limit the destruction. Let's say somebody actually logs into your machine, gets into your machine. You want to be able to limit how much they can touch and how much they can do and how much they can see. And Linux has certain types of capabilities of doing that. You can change the root location so you can create a jail for these people to be executing in. They can't see the rest of the system. They can't execute certain commands. They can only execute the things that are inside of their jail. You can create containers and virtual machines for them using a hypervisor like KVM or Zen, or using a virtual machine like VMware, and people can then execute their programs inside of that container, and anything that happens inside of that cannot get to the outer side of the machine. This also allows you to have regular users inside of the VMs reading their email and things like that. And if they unleash a worm or if they unleash some type of virus, it's only inside of that VM. So you could then get rid of the entire VM and protect the rest of your system. You can use other types of facilities like Lightwork Directory Access Protocol to set up your own types of systems for protection. And the SMB Sandbox software can allow you to set up a file and print server, a very secure one, even to support your Windows systems or BSD systems or other Linux systems or Apple systems as a file and print server. Now, there are some distributions that are very security oriented. The whole thing is about security. Whonix allows you to hide the IP address of the system so that people don't know. When you send email and things like that, they don't know the IP address of your system, and so therefore it's very hard for them to attack your system over the internet. This software actually works on Windows, Mac OS, and Linux. It's not just a Linux thing. However, Cube's OS, a Fedora-based system, actually includes this, and you can set up a very secure system using Cube's OS. Tails is another system. It allows you to take a USB thumb drive and set up a live distribution of Linux with persistence being optional. Persistence means if I create data, I can store the data on the USB thumb drive. So I can walk up to a system, stick the USB thumb drive in, reboot the system off the thumb drive, work with it live, and then store my data onto the thumb drive, shut the system down and pull the thumb drive out, and the original system that was there, whether it be Windows or whether it be Linux or BSD, is still just the same as it was. And there's other distributions that work this way, and you can find them on the internet. There's also tool-based distributions that help you test other systems to see if they're secure. Kali is probably one of the most famous ones of this, as a series of tools used by people that some people call them white hats and some people call them black hats or hackers or crackers. Doesn't make any difference. These tools can be used to try and break into systems and test them for the security. Parrot SecurityOS is another distribution like this, and there's others on the internet. Now, all of this has just been using Linux and the tools that are in Linux to try and create a secure situation. What you also want to do is think about configuring minimum systems to do the job. Because the more software that's in your operating system, the more chance that there is some hole or some trapdoor or some method of breaking into your system. By having the least amount of functionality to do the job means that you can cut down on the attack vectors of getting into the systems. You also want to limit showing yourself to the outside. Don't automatically run a database engine and open it up to the world, because people would see that and be able to try and attack your database system. So keep the things that you expose the outside world to a minimum. I love IPv6. IPv6 has 128 bits of address space, and in some implications from ISVs, you get 64 bits that is yours, that you can do anything you want to. So as you're setting up in your network different devices, you have 64 bits of address space that you can have an address for each device that you want to talk to. So people say to me, well, how big is 64 bits? 32 bits is 4 billion bytes. And that sounds like a lot. You could have 4 billion machines. That sounds like a lot. But if you have 64 bits, then it's 32 bits times 32 bits, or 4 billion times 4 billion. And it's a number that's so large that if you accessed an address every second of the day, every day of the year. You could do that for 584 years and still not get every address. And if what you do is you move the addresses of your machines around inside of that 64 bits, you're going to frustrate hackers a great deal because there's just no way they're going to be able to attack your address space and find your systems inside of that. In addition, the address space is for each system. You typically have ports that you have to connect to inside of that address space. And if you start moving your ports around or having them in places that are not what people would think of as being normal places, that adds an even greater amount of time it would take for people to break in. So there's lots of things you can do with open source free software, and if you're the systems administrator of the system. In addition to all of this, you can set up a honeypot, which is a system sitting on your net, really doesn't do anything. It's just something that would attract the attention of somebody trying to break into your network. And once they go into the honeypot, they think they've broken in. But in reality, they're not doing anything. And so you can keep them there, keep them busy, then track them down. And like my friend, get the FBI on them. With all of that, I'd also like to talk about multi-factor authentication. People used to the fact that you log into your computer system, you give your login name, and you give your password. Your password is the first level of authentication. So you authenticate to the system by giving your password. If your password is correct, it lets you in. That's wonderful. But as most people know, passwords are a pain in the butt. In order to be good, you need to make your password fairly complex. But that makes it hard to remember. I actually never use passwords. I only use passphrases. And so in my mind, I know what the passphrase is. And if I type in that passphrase, it is very, very, very unlikely that somebody would ever guess it. But there's a possibility. So what we do is you say, let's have two types of authentication. Multi-factor authentication. Well, it could be if your laptop has a webcam in it that you could do facial authentication. And so that, in addition to your password, makes things more secure. But people can spoof that by holding up a picture of you. And so then you add fingerprint authentication, because some computer systems have a fingerprint reader. And between your facial authentication and the fingerprint authentication and you knowing your password, that's even better. You could have authentication based upon where you are. Are you in your house? Are you in your company? Are you, and if you are, then that's another form of authentication. So this authentication I'm showing here on the screen is a key. It fits into your USB port, or perhaps if you're using it with a phone, you can access it through MFC. And this particular one is made by a company called Solo Keys. It's open source. It has open source firmware. It has open source client-side software. And it even has a system that can give you a time-based one-time use password for things like Internet of Things, if you need that. And this is completely open. You could make this if you had your own surface mount technology machine. They publish all the things necessary to do that. But you could also buy it from them for a relatively low price and use that in your authentication method. Another interesting project is called Freedom Box. This is at freedombox.org. It was started by a friend of mine named Evan Moglen. He is a professor and a lawyer at Columbia University in New York. And about 10 years ago, Evan started thinking about server systems and are they really secure? And he decided to start this Freedom Box project to make a system that's completely free of binary blobs. No binary blobs in the hardware, no binary blobs in the software, and in addition would be an easy to set up and maintain server system where you would keep your most secret and most precious of things. So, for example, your credit card numbers, your birth certificate, an image of your passport, all of the things you don't want other people to see. You don't want to send them to uh, Google. You don't want to send them to AWS. You don't want to send them to Azure. You don't want to send them outside your country where other people who we dare not say their names will be looking for that type of thing. And if you buy the little single board computer or use another single board computer and attach a little 2.5-inch hard disk drive or SSD to it, you can create a nice NAS system to run your other systems in your house on that. All of this software for doing FreedomBox is actually included in Debian 10. Or you can go to the website and pull it down and put it onto your own distribution of Linux. And it's a very nice little system. Here's some of the functionality that FreedomBox allows you to have. You can set up your own VPN. You can set up your own Tor server. You can set up a virtual private network. You can do all sorts of things in the software that comes with this. And it has a little front end to it that makes it very easy to set these things up. Now, on top of all of that, of the software that comes from FreedomBox, there's also another concept that you can do, and that is called federated social media. So instead of using something like Facebook, which looks at all of your data and maybe makes decisions about your data and presents things to you in a certain form, these social network pieces of software allow you to set up a social network that's federated. It's not held, the information is not held in one place, it's held in a bunch of different places. And so you can be sure about what software is being exposed to other people because you have control over that software. And other things you might want to think about is setting up a gateway or a firewall to do packet filtering to see what type of packets are actually going outside of your network and what packets are coming in. You can set up DMZ zones if you want to have some type of a Wi-Fi hotspot for somebody, but that's outside of your network, of your protected network, and that is controlled by your firewall. There's various types of distributions of Linux that allow you to do that relatively easily. As I said before, you can set up a VPN, or you can use DNSSEC, which senses where you're going for your DNS information and makes it much more secure than just using a regular DNS server. Another thing you need to think about is the training of your users and network systems admins in security. This is very important. People have to know what is out there that they can use to make their systems more secure. They have to know how to use it in a secure fashion. And you can either take a course in this or everything, or you can just, allow the people to study it on their own and then take a certification test to make sure they know the proper answers to these different types of problems. And I'll give a very blatant advertisement that I am the board chair of the Linux Professional Institute. We have a certification for security, and you can go to our site. You can see what the objectives of that are. An objective being things like set up a VPN, set up a Tor. If you know how to do that, then you're probably in good shape. If you don't know how to do that, then maybe you need to study more. So the prognosis, which I've left for last because it's kind of depressing, is that the antagonists in the old days used to be script kiddies. But now there's many more of them. The internet is faster and it reaches further, and we have a lot more users that don't really understand anything about security. So it opens it up. And as we've seen in the last several weeks, the people are getting really serious about this. Ransomware has shut down things like gas pipelines and disrupted supply chains and, gotten millions of dollars out of people because they wanted to have their data back. And this is not only foreign domestic terrorism, or foreign terrorism, but domestic terrorism. People inside of our own countries are using these techniques to try and gain control of the internet. And there's people who aren't really trying to break into your systems, but they are selling the software, the tools that do break into the systems, so as you know, so they can make money. And they charge a huge amount of money for these software to do this. And then, of course, we have my friends, Paul and Sam. And if you live in the United States, like I said, you might be protected by our Constitution. However, as a U.S. citizen, if I talk to somebody in Brazil or I talk to somebody in Uruguay, then that protection disappears. And people can look at what I am doing because I could be a spy. So you have to protect yourself no matter what. You have to force them to go to a court, to get that subpoena, to come to your house, and they have to tell you what they're looking for. And then, of course, that's the NSA, which I like to think are actually the good guys. But then we have other people that may not be as good. I want to stop for a second about real computer security and talk about the security of your country. Would you be able to make computers if something was to happen to Taiwan? Would you be able to make computers? Would you be able to get all of the computers you need if China decided that they were going to create an embargo against your country? Would you be able to duplicate everything you need if Microsoft in Redmond, Washington, was to be blown up by an atomic bomb or get hit by some type of virus that could kill off everybody, and therefore you wouldn't be able to get new copies of Windows out for a very long time? And who do you trust? Microsoft sets up centers all over the world that they say, oh, come to our center, don't bring your laptop, don't bring your notebook, don't bring your camera, but you can look at all of these, look over the net at our source code pool, and you can see the source code that we use to build Windows 10. Now, if you believe, if you trust that software, that you're in that building in, say, Brasilia, that the software you see is the software that actually made your distribution, then I have a bridge to sell you in New York City, because it doesn't have to be. And so, and even if it was, what version of the software is it? So you need, if you really want to trust it, a trusted person in your country to be seen over the build process, to look at the source code before you go into your system. And you have to ask yourself, who built your computer? Who installed your BIOS? Who built the CPU? Is the microcode okay? And even if all of that is done, where do you stand in the allocation of resources? Is your country a friendly country to China? Are they going to say, oh yeah, we're going to give you all the resources you need, and we're going to let this other country be at the end of the line? And what happens if, as I said before, China was to create an embargo against your country? Can you say the word Cuba? My country, the United States, has had an embargo against Cuba for 60 years. So long that most people in the United States have forgotten why we have the embargo against Cuba. What if that country was yours? That's the question you have to ask yourself. All of these things are things that keep me awake at night, in addition to bad beer and bad scotch, of course. And the Internet of Things makes this even worse. Infrastructure issues with the grid and with pipelines make it even worse. So you have to ask yourself, who do you trust? And this is one reason why we started the Caninos Lucas project in Sao Paulo, Brazil, in conjunction with the University of Sao Paulo and LSI Tech, to design and build an entire system with no binary blobs, with everything being able to be audited, with the technology shared and spread and inspected and audited with everybody so everybody could be looking at it. And in addition to that, the University of Sao Paulo is a certificate authority, so they can create certificates of authority for names on the internet and in order to boot a UEFI system that is made in Brazil. And if you are really paranoid, you could obfuscate your own instruction set, change it slightly, and then recompile the operating system so it only works on that computer. It's really not that hard. And I am not paranoid, believe it or not. I'm not paranoid because my conspiracy theories are true. And I'm diabetic. And I'm fat and I'm old. And I've had 3 heart attacks. So I'm not going to be around much longer. But I did take my COVID booster. I'm not going to be around much longer. You are the ones who are going to have to worry about this. And a final word to the CFOs, CIOs, CTOs, all the people up there. You have to architect your security. It isn't going to happen magically. There's no single magic bullet to any of this. No system is completely secure. And what you want to do is make yours so secure, so hard to break in, that people will choose another system. They don't have the time to try and break into your system. You need to treat your system and network admins as an asset, something that's valuable. It's not just a necessary expense that you have to pay. It's something that you need goods of. Here are some references that I've used in making this talk, and they can help a lot if you're trying to put together your architecture. With that, I thank you very much for listening to me. My name is John Mad Dog Hall. I am the board chair of the Linux Professional Institute and the president of Linux International, as well as the chief advisor and co-founder of Caninos Locals.